Today, I'm going to talk about the finite source mechanism solution of the Samos earthquake. Okay. All right. We're going to talk about the earthquake in October the 30th, but in general, we are experiencing many offshore earthquakes in Aegean Sea. Geodetic measurements are not very sensitive to far-field deformations, so it's generally a technical challenge to get some coseismic deformation and to process and analyze these coseismic observations. For one thing, inside observations are generally partly available and sometimes not available at all. And GNSS observations, the network in offshore, near the coastlines are not sufficient to provide sufficient constrained parameter space. So we started just a re-survey of the available network just after the earthquake in 1 week. And after that, in this observation schema, we collected 62 sites, and we obtained 62 sites coseismic offsets. And after that, we modeled the coseismic offsets for both uniform and distributed slips. Our uniform slip model shows a finite source of 43 kilometer long and 16 kilometer wide rupture, which slips 1.42 meter on average. We're going to talk about that later. And that rectangular finite fault lies back down to 13 kilometer depth. And we also observed some close sites to the epicenter were not able to be modeled, sufficiently. So we provide the distributed fault model, which provides a nearly perfect fit to the observed surface displacements. You'll see some the area of interest at different zoom levels, and the fault lines and the delineations, let's say, come from different sources in the literature, about 20 different sources. The offshore delineations are mostly based on seismic profiles, and also in the length, some faults were obtained from active fault map and many other literature studies. In the right, upper right and lower right figures, you will notice that the available fault delineations does not necessarily coincide with the result geometry, which is about which lies in northeastern and northwestern and southeastern direction. And in the lower right figure, you will see some historical earthquakes in black asterisks, mainly from the 19th century. And this is the sort mechanism from different centers, and we also included our solution in this table. Our GPS solution is the first one here, and tips are more or less similar. In solutions it's about 4 to 5 degrees, and strike is also seems to be our solution is a bit. It's compatible in general, but it's usually 20 degrees tilted from the east-west direction. And GPS is these are all point sources. These are all come from seismic solutions. These are all seismic centers, and this is finite solution, so there's no auxiliary plane here. So the latitude and the longitude corresponds to the centroid of our rectangular fault, and this is strike. And yeah, it is mostly normal faulting with a little bit lateral component. And this is the depth of the lower edge of our rectangular fault. And this figure also shows the aftershocks. This is the Menderes graben. It is the largest graben in Turkey with an extension rate of about 6 millimeters per year. And since this is graben and the obtained solutions is a normal faulting mechanism, it gives the impression that these donations should be compatible with this one in length, or The fault traces just in the northern part of Samos Island is just westward continuation of this mantle graben. And these are the sites we used for collecting observations. We have various both continuous and campaign type sites, and course TR, which is a national continuous GNSS infrastructure, let's say. And Turkish National Fundamental GPS Network. This is not a continuous network, but it is the first order network of Turkey, providing very precise, both good stable monumentation and historical record. It goes back to 1997, and these are just simple sample pictures. And these are the observations. And total, we have total 62 sites, 29 campaign sites and 33 continuous sites. All the campaign sites were observed at least 8 hours with 30-second sampling interval. And all the observations took place between 5 and 8 November. So it is just in 1 week. So we didn't let post-seismic deformation go on or interfere with our observations. And all the GNSS data were collected and processed with Comet Globkey software with the state-of-the-art models. All right, this is a figure for my continuous site. I mean, Izmir and Menteş sites in the Karaburun Peninsula. And for continuous observations, we have more epochs before and after earthquake. And instead of differencing the closest epochs here to get the seismic displacement, we divided our domain, the time part, in pre and post parts, and we averaged both the pre and post parts to minimize the noise and increase the precision for all three components. This is east and this is up. And this is the first order picture of the observed and modeled displacements. As you see, there's the closest sites in Samos Islands are not modeled very well. On the other hand, the far field sites, these areas are a little big, so actually this side and this side, they're about 100 kilometers. So it just constrains the attenuation of the model, which is directly sensitive with the length and the general mechanism of the fault. We used the elastostatic green functions, Okada 1985, and we didn't allow any tensile component, no opening, so only strike slip and deep slip were allowed for the inversion process. We downweighted the vertical offsets about 1/3 of the original uncertainties, which corresponds to about 10 times variance downweighting. And for the optimization, we use a hybrid approach, which employs simulated annealing, which can avoid the local minima. And afterwards, we used an efficient algorithm, BFGS, it is derivative-based method. The objective function is the weighted residual sum of squares. So we employed the full covariance structure of the observations. In this two-step approach, we first inverted the fault geometry, keeping the slips on the faults constant, actually just 1 meter. And after that, we modeled the slips. And this plot shows the trade-off of the parameters. Actually, each dot here, it's an experiment consisting of 100 different experiments. And each dot here actually corresponds to one experiment, one inversion. And using the original coordinates matrix, their error estimates, we produced 100 different observation data set and inverted them one by one to examine the trade-off between parameters. Here, the moment is not an independent parameter since the slip is fixed. It's almost the parameter here. All right. And this is our distributed fault model. As you see, even the closed sites are modeled very well. That seems to be an observation error at this point. Otherwise, it provides a very decent fit, let's say. We use the modified Lancaster inverse scheme to for the distributed slip model. This step is completely linear but ill-conditioned, as you know. So we constrained our model with some roughness constraint, and use the steepest descent minimization method to get the slip at each patch. These are the patches. As you see, generally the slip is concentrated in the western part of the fault, and all the slip is really limited to the 12 kilometers, first 12 kilometers, and at larger than 1 meter slips are limited to a 7.5 kilometer step. These are in different three-dimensional perspectives. All right. In accordance with the north-south extension tectonics of the Aegean region and coseismic displacement calculated from the geodetic data also confirm a pure north-south extension, just very small, like that little slip was also obtained during the inversion. But we can say that it's pure north and south extension. It's a north dipping fault, by the way. And the largest movement caused by the October 13th, 2020 Samos earthquakes. The magnitude is also discussed after every earthquake in Turkey. Our geodetic inversion shows a moment magnitude of 6.9, and the largest movement was also at Samos station, and it is the closest station to the epicenter of the earthquake. And similar results were obtained in the studies, in some of them about earlier reference cited in the previous slides presentations. And the largest coseismic displacement is 136 millimeter at the north component, since it's a north-south normal faulting. And yes, our strike is 288 degrees, which is consistent with the findings of other researchers, and also consistent with other seismological centers. The coseismic inversion of dense GPN array in the study reveals a finite source of 43 kilometer length fault, and which is close to the estimate of ALIS et al. 2021 of 37 kilometers, but it's 1/2 of 80 and 100 kilometers given by Doğan et al. Our estimated width of the fault in uniform model is 16 kilometers. This uniform slip modeling is very useful for it provides a comparable outcome of the results. All right, and okay, but we also show that a uniform slip model is not enough to account for all the observed displacements in the field, so a distributed slip model is needed, at least for our study. If it weren't for TÜBİTAK, we wouldn't be able to carry out these observations, so we would like to thank TÜBİTAK for the rapid financial support just after the earthquake. And also, this project was supported by Afyonkarahisar University Scientific Research Foundation, and also TÜBİTAK. We already said that. And we would like to particularly acknowledge the data for this study. These are the continuous sites, Turkish COSTR, Turkish National Continuous GPS sites, and private Greek networks, SmartNet, and for providing the data. And also, we'd like to thank many individuals who took part in the field observations. Mainly, these are students at both undergraduate and graduate level. Thank you for your patience and interest.
Okay, thank you very much, Professor Aktuğ. So we have time for discussion or any questions. We have completed earlier than scheduled program. Any question you can ask also live from the panelist list. I can't see any question from the Q&A section or chat section, but we have time, and I can see a question for Alexandros Chassipetros for the earlier talk. Are you there, Alex?